Assalamualaikum warahmatullahi wabarakatuh. Today we're going to discuss about engineering design, modeling of dynamic system for mechanical system. So what is a mathematical model? So mathematical model consists of two elements basically. Law of conservation, which is Newton's second law, as well as a law of properties, which is each element of the mathematical model. So how to represent a mathematical model? This mathematical model could represent using a differential equation, transfer function, state space, or in the block diagram. Okay, so this is an example for differential equation where you got dy dt. It's actually y dot. We already learned this one in mathematics and control system as well. Right, so this is an example. For example, you've got d square y over dt square plus 3 dy dt plus 10y equal to 10. You can note that it as y double dot plus 3y dot plus 10y equal to 10. Right, so for transfer function, basically you need to do a Laplace transform from your y dot. Right, so this is an example. So you have a previous example, and then you noted as a y dot, and after you Laplace transform this equation, you can get s square ys plus 3s ys plus 10 ys plus equal to 10 us. Us is actually the input. Alright, so this is the state space where you can represent the mathematical model in the state space as well, where on the left hand side you've got x dot equal to matrix, transformation matrix of x plus another matrix of your input. So this is the block diagram, another representation of the mathematical model. So you can see from the block diagram here, you use a Laplace transform as part of the block diagram. So for the modeling, we got a law of conservation and law of properties, where the law of conservation is the Newton's second law. And then for the law of properties, you got three elements, which is a mass, a damper, and spring. Basically, for the mechanical system, you got two type of motion, which is a translation motion as well as rotational motion. So for the second Newton's second law, for the mass, this is the formula used for mass, where summation of force equal to m d square x over dt square. This one if the for the translation in the x direction, right? So if you've got in x direction, you got d square dx over d square x over dt square. So if you got in the y direction, so if your variable is y, so you can note it as a d square y over d dt square. Alright. Okay, so for the rotational motion, you got summation of torque equal to j d square theta over dt square, where theta is the variable for the rotational motion. Right. So rotational motion could be anti-clockwise or clockwise direction. So this is the example for the spring. You can get a translational motion for the spring as well as rotational motion for the spring. Okay, for a translational spring, first of all, you need to draw a free body diagram. In order to use a Newton's second law, you need to draw a free body diagram. This is the free body diagram, where you've got point 1 and point 2 as well. Right, so for the point 1, you got x1. For the point 2, you got x2. Right, and the force is in the free body diagram, you got opposite direction. Right, so if you define your positive direction is towards the right, is the positive. Right, so your force for the spring actually is equal to k x2 minus x1. Why minus? Because the direction of the force in the x2 and then x1 is of opposite direction, right? Force in the x2 is towards the positive, and then force in the x1 is towards the negative. So that's why minus. If the force in the x1 is towards the positive as well, so you need to plus in this formula. All right. Okay, so for rotational spring, you got this formula where torque is equal to kt theta. So if you got this spring, you got torque here, and then you got theta here, you got kt theta. But if you draw a free body diagram for this spring like this, right, you got t in this direction, so there's another t in opposite direction in here, where you got here is theta 1, and then here is theta 2. So your formula will be become t equal to kt theta 1 minus theta 2, right? So this is an example for the spring. You can try to create the formula from here. Right, so this is a damper, a typical example of a damper, where damper is actually the force in a proportion to the difference in the velocity. So if the spring is related to the position, damper is related to the velocity of the item, of the mechanical movement, right? So this is another example. So the formula you're going to use for damper is this one. F equal to C x2 minus x1 dot x2 dot minus x1 dot, right? So this C here is the damping constant. Sometime in other book you can denote it by B. Some other book denoted by D, right? So is the C is just a constant here, right? So it could be B or D. It's depend on which book you are referring to. So to modeling a mechanical system, this is the process. First of all, you need to do a schematic actual of physical system into mass, spring, or damper. What does that mean? For example, if you want to do the mathematical model for the human skin, for example, right? Human skin can be represented as a spring because it got stiffness there, or there's some damper as well in the human skin. So you can represent as spring and damper as well, right? So not necessarily if physical spring or damper exists in your system. And then there will be a variable which is x for translational, or theta for rotational. And then after that you need to draw a free body diagram. After you draw a free body diagram, you need to indicate all the forces on the body, right, to indicate the acceleration. Basically, Newton's second law is related to acceleration, and then after that, then you can apply the Newton law for translation or rotation. It depends on the mechanism. And then, of course, you need to eliminate all the internal forces in the system. Okay, this is the example where you got a door frame and a damper in your system. All right, so you can represent this. This is the free body diagram. You can see here you got a damper for the screw, for the hole, and for another hole. These two hole is actually for these two hole here, right? For the damper. But basically, to simplify this one, you can combine all these three damper into one damper, where you got a frame, and then you got a damper, as well as you got a spring. So you can draw like this as well, right? Instead of you represent by the each hole as one damper. So this is considered as C, which is the summation of the all three damper here, and then you got mass here. So this is how you draw a free body diagram. After that, you have a X for your variable. If you separate the spring and damper and mass, for you can draw the mass as individual mass. You got a force here, which is the external force, and then you got another force for damper, and then another one for the spring, right? So if you do you look at the mass, you can use this formula for the mass. I can go back to the this slide. Okay, this one. Okay, you need to use this formula because it's a translational motion. All right. Okay. So the summation of force equal to m d in this case is indicated by x, right? Okay, so d square x over dt square. Right, so this is the formula for this equation, but the summation of force here is equal to, if you indicate the toward the right is the positive, so you can have the f minus fc minus fs equal to m d square x over dt square. Right, so this is your equation 1. And then from the damper and the spring, this you got k. So from the damper you can have for example, this one is this one is a frame already. So for the damper, fc equal to c x dot, right? X dot. Why there's no x1 minus x2? Because the x, if you consider this one x2 or this one is x1, x1 is actually equal to 0. So that's why there's no minus here. Right? So that's because this one is ground already. So that's why your fc equal to cx dot. And then your fs, force in the spring, is equal to kx. So if you insert both here, the equation 2 and equation 3 into the equation 1 here, you can get f minus c x dot minus kx equal to m x double dot. When you rearrange this one, you can get m x double dot plus cx dot plus kx equal to f. Right. So you can see here this equation is similar to the example in the transfer function. What is it? In the differential equation here, right? Where you got y dot equal to plus 3y plus 10y equal to 10. So this is the kind of representation for this system. Where is it? Yeah, for this mechanical system for the damper, and they got a spring as well inside here. So this is the answer, right, for the differential equation. Okay, let's look at another example. We have a car suspension system here, where this can be represented the car, the suspension of the car. This M is the body of the car itself, and then Y is the road profile, right? When you try to draw a free body diagram as before, the M is here with the force in the for the damper, and then force for the spring, right? So when you want to do the calculation, summation of force equal to m x double dot, right? Because the movement of the body is considered as x, right? So x double dot. So if you look at the spring, right? You got x here, and then from here is actually the road profile, which is a y, right? The same thing if you look at the damper, you got x here, and then the road profile is your y. Alright, so if you want to calculate from the spring, force of the spring should be equal to k. Upward is a positive, so this one is the negative, so it's always opposite direction, right? So k x minus y, and then for f damper is equal to c x dot minus y dot. Right, so you insert both here into this equation, then you can get and then of course from here this one is does not finish yet, because if you look, if you define x upward is as a positive, right? Upward is as a positive, so you can have a minus fs minus fd equal to m x double dot. This is equation 1, this is equation 2, this is equation 3, right? So you insert 2 and 3 into 1, right? Then you can get minus k x minus y minus c x dot minus y dot equal to m x double dot. So when you rearrange this one, you can get m x double dot plus c x dot plus k x, right? So because both of here you move to the other side, should be equal to minus become a positive again, equal to c y dot plus k y, right? So basically this is the the what we call it, transfer function for the for this system, or you can call it the mathematical model for the suspension system of a car. All right. Okay. So basically, all right. So there's this another example for a rotational system. You've got a bar here, a bar, and then this one is rotating at the theta direction, right? And then even though you do not have a spring here, so you can represent this bar as a spring, as shown here. All right. And then if you want to calculate the torque here, torque should be equal to kt theta, right? Because there's no theta on the other hand, right? So basically this is the equation for this system, right? Okay, so here is another example for rotational system, where you got a disc here rotating on a bar, and then you got CT damping here as well as here, right? And then this one is rotating at a speed of omega, right? So if you try to draw a free body diagram, you can draw like this, okay, where omega is the rotational speed, and then T is the torque, output torque into the system, and then you got F here, and then CT omega, and then they got two CT omega, which is represent this one as well as this one. All right. So if you want to write down the mathematical model for this system, you can write the summation of torques equal to I omega dot, right? Omega dot is actually theta double dot. Okay. So the summation of torque is, if you take the clockwise is as a positive, clockwise is a positive, so you can get a T minus FR minus bigger R here. This R is this the radius here, right? This R, and then minus CT omega minus CT omega, and then should be equal to I omega dot, right? So if you rearrange this one, so you can get I omega dot plus 2 CT omega should be equal to T minus FR. Okay, so this is basically the mathematical model for this system. Okay, this one is another example, so you can try to solve this one by yourself. So if you have any problem, we can discuss in the next synchronous class, right? So this one and this one, I want you to solve by yourself, right? Try to solve it, right? Because if I solve everything for you, so you never learn, right? If you try to solve yourself and then you can go back to the slide that I show you, then you can get idea how to solve it in the exam or in the quiz later on, right? So this is another one. Okay, I want to go to the Lagrange method, right? This is another method. It's you can create a mathematical model as well using a Lagrange method. But the advantage of Lagrange method, you no need to have a free body diagram, right? Right. So in the Lagrange method, what you need to do, you need to create a Q as your variable, right? As your minimum number of independent coordinate. If you look in example, you will understand better, right? So you got a force or torque in your system. Okay. Okay, this is the general equation for Lagrange method, right? T here is the kinetic energy. Basically, the Lagrange method is you dealing with the energy, right? Energy. Previously, you dealing with the force. Now you dealing with energy. All right. So if you differentiate the energy, you can get force basically, right? So partial differentiation of the kinetic energy. This is kinetic energy as well. This is a potential energy. This is a dissipative energy. All right. And then F is external force. Q is generally the variable that you dealing with. Variable is something that change with time. All right. So T, which is kinetic energy, you already know, half mv square, right? So or you can get this one is in the translational motion. Half g theta dot square is for the rotational motion, right? And then for potential energy, half kx square for what we call it spring, and then this mgx for uh, potential energy for a mass, right? For a mass. All right. So dissipative energy is basically for the damper, right? For damper, you got half cx dot square, right? All right. Let's look an example. This is the mass spring example. You got a mass m here, and then the spring k, and then you got x here. There's no damping here, right? So what you need to do, you need to use okay, in here it shows a different method, but never mind. We're going to create a new one based on this equation, right? Based on this equation. First of all, you need to write down this equation where d over dt. Okay, just copy paste this equation, right? So where d over dt, partial differentiation of t over dq I dot minus partial differentiation of t over dq plus the partial differentiation du over dqi plus d over dqi equal to f, right? This one is a dqi dot. Alright, dqi dot equal to f. So basically this is the equation that we're going to use to calculate this one. But since there's no what we call it, the no damper, so this part become 0. There's no external force, so F equal to 0 as well. So what we left is the potential energy as well as the kinetic energy. T is the kinetic energy. The kinetic energy T should be equal to half of m x dot square. right? So that's basically a kinetic energy. And then potential energy, U equal to half of K x square, right? So this is the formula, right? So this one is the potential energy, and then this one, the one that we used just now, is potential kinetic energy. This one is potential energy, right? So after, if we want to insert here, we need to differentiate, partial differential the kinetic energy here. So what you need to do, you need to dt over dq I dot, right? Q dot here is actually x dot, right? So basically what you need to do, you need to dt over dx dot, and if you differentiate the x dot here, you can get m x double dot, right? So that one, this part. And then if you want to find this one, actually you want to find the partial differential of kinetic energy over dx. But in here there's no x, right? There's no x, so it become 0. Okay, and then this part du, you want to find this one, right? Du over dq, or du over dx. So there's x here, so that one become kx. All right, so you insert equation 1, equation 2, equation 3 into this general equation. Basically this general equation, you can get basically this one. It should be equation 1, equation 2, 3 and 4, right? So you insert 2, 3 and 4 into 1, right? So you can get d over dt of this one, right? Mx, no, sorry, that's not mx double dot, is actually mx dot only, right? Mx dot only. It's only one dot. There's no double dot, because this one we differentiate. Uh, we differentiate the x dot, right? We do not differentiate with the time yet, so it's actually mx dot, and then minus 0. Basically this one equals to 0, plus, and then this one is kx, right? Plus kx equal to 0, right? So if you differentiate this one with the time, so you can get mx double dot plus kx equal to 0. So you can have this equation basically, right? This one is a different this one is still a Lagrange method, but different approach, right? You can use this method if you want, but I'm not going to touch this method, right? So basically this is the uh, mathematical model for this type of question, right? Using Lagrange method, right? So for example, this one, you got a mass, you got a spring and damper. In this example, you got damper as well as the external force. Ft is the external force. When you first of all, what you need to do, you need to write down the Lagrange equation, right? Partial du over dq dot, right? And then minus du over dq plus, no, this is not du, this one is dt, right? Because t is how am I gonna delete this? Point option eraser. So I'm gonna delete this one. Point option and okay, dt. This one dt. This one plus du over dq. and then plus dt over dq dot, right? Q is the any variable. In this case, we got x as well. So basically, dt over dx dot, dt over dx, du over dx, dd over dx dot, right? So equal to f, right? F. So it is already given here, kinetic energy equal to this one, and then V is potential energy. Potential energy is kx dot kx square plus mg h plus x, right? So basically this is the potential energy. Uh, oh, okay. This is another method because you calculate the kinetic minus potential energy. This one is okay. This one is basically the damper. What you need to do? You just insert this one. This one is the first equation. This one is second equation, third equation, and fourth equation, right? And then okay, you need to differentiate this one. Uh, okay, d over dx dot should be equal to m x dot, right? And then if you try to calculate uh, okay, dt over dx should be equal to 0, right? Because there's no x here, it's only x dot. So du over dx should be equal to kx will be plus mg, and then mgh, if you differentiate with the x, you can get 0, right? Right, so if you want to calculate the dd over dq dot, right, so basically dd over dx dot should be equal to bx dot. Okay, so you insert all these. Oh, basically this one is the equation 2, 3, and 4. Right, so you insert into 1, then you can get d over dt of mx dot minus 0 plus kx plus mg plus bx dot equal to ft. Right, so if you differentiate this one, you can get mx double dot plus kx plus mg plus bx dot equal to ft. And when you rearrange that, you can get mx double dot plus bx dot plus kx equal to ft minus mg. Alright, so this is basically the mathematical model for this example. Alright, okay, you can compare this one, this answer to our answer just now, because this one is equal to f, right? Okay, so this one you can try to solve by yourself. This one I want you to try by yourself, right? And this